Very good morning, everybody. This is Prerna. So today we are going to start. We are going to revise the chapter P block. As you know that uh, we are revising these topics for upcoming NEET. So today we will revise P block. Okay, fine. So before starting this chapter, before starting the revision of this chapter P block, I just want to clear few things. First thing, that you do not have to read everything blindly which is given in the NCERT. We have to stick completely with the syllabus given by NTA. So I have brought one screenshot of this portion which we have to follow, and I will request you guys also that follow the portion which is given by NTA. Accordingly we have to prepare, as we know that we have already less time and we can't afford to waste our efforts on reading extra. So just have a look here. So this is the portion. So let's just understand the portion, then we can start the revision of this chapter. Electronic configuration and general trends in physical and chemical properties of the element across the periods and down the groups. So in P block from group number 13 to 18, we have to stick with just general physical and chemical properties across the period down the group. Then unique behavior of the first element of the each group. Okay, so these two things we have to focus on, these two things, and accordingly we have to revise this chapter. Okay, so just start this. Let's start this. Okay, so we are starting this chapter P block. P block starts from group number 13 to group number, it goes up to group number 18. Okay, so we will start this we'll start revision of this lecture P block. Okay, so group number 13, I would suggest you guys that it is very difficult to remember, but if you remember these elements sequence wise, it will be very helpful. So group number 13 is boron family. Group number 13 is boron family. Boron, aluminium, gallium, indium and thallium. Group number 14, carbon family. Group number 14, carbon family. Elements are carbon, silicon, germanium, tin and lead. Group number 15, nitrogen, phosphorus, arsenic, antimony and bismuth. Group number 16, oxygen, sulfur, selenium, tellurium and polonium. Group number 17 is fluorine, chlorine, bromine, iodine and astatine. Group number 18 is noble gas, neon, argon, krypton, xenon and radon. Fine. So we have to study, this is the elements from group number, these are the elements of P block. Okay, fine. So these are the elements from P block. Okay, so what we will see first, boron family has no special name, carbon family also. Nitrogen family, they are called nitrogens. Nitrogen family, they are called nitrogens. Group number 16, they are called chalcogens. They are called chalcogens. Group number 17, they are called halogens. And group number 18, they are called noble gases. Zero group element, rare elements. What are the other names? Noble gases, zero group, rare element. Correct? Yes. Okay. So this is the whole element sequence. I would suggest you people that better you remember these sequence. It will help you a lot. Okay. Now Let me tell you one more thing. In this lecture, first we will revise the theory and then we will go to the question practice. So just I'm telling you this so that you will know the sequence. So today we'll revise this chapter, then we will solve the PYQs and the important questions which can be asked from this chapter. Okay. So what is the configuration for boron family? What is the general electronic configuration for boron family? NS2 NP1. I am writing general electronic configuration. For carbon family, NS2 NP2. For nitrogen, NS2 NP3. For oxygen, NS2 NP4. For fluorine, NS2. For halogen family, NS2 NP5 and NS2 NP6 complete octet. Right? You guys might have seen that in the portion one in the P block syllabus there was given anomalous behavior of first member anomalous behavior of first member of each group. Anomalous behavior of first member of each group. So who is going to show the anomalous behavior, whose behavior will be different from their respective group? So let me tell you one thing. For example, boron 13, all the elements in boron 13, they should show same behavior. This we know because they all will have the same valence electron. I am writing for this for all of them. You can write and you can understand on your own. So this is 2s2 2p1. This is second period, third period, fourth period, fifth period and sixth period. 2s2 2p1 valence electron 3. 2s2 2p2 valence electron 4. 2s2 2p3 valence electron 3. 2s sorry, just a second, this I am writing it wrong. Wait. 2s2 2p1 outer electronic configuration, 3s2 3p1, 4s2 4p1, 5s2 5p1, 6s2 6p1. Okay, so they all have the same number of valence electron, which is 3. They all are following this pattern. What is different? Just the n value, correct? They all are following the same pattern. They same number of valence electron, 3 3 3 3 3. Only this is different, which is the period number. For thallium it is 6 and for indium it is 5. So what we tell that if the valence electrons are same, their chemical behavior should be same, right? So for a group, all the elements should show same behavior. Not only for group 15, this we can tell generally, but elements of the same group, they should show same behavior. But what happens? First member of each group. Who is the first member? Boron, carbon, nitrogen, oxygen, fluorine and neon. First member of each group. They will show different behavior from their respective group elements. Okay. So who is going to show anomalous behavior? Boron, carbon, nitrogen, oxygen, fluorine and neon. Okay. So let me discuss this with you people in the next slide. Anomalous behavior of first member anomalous behavior of first member of each group. Okay, so what are those elements? Boron from group number 13, carbon from group number 14, boron carbon, nitrogen from group number 15, oxygen and neon. They all are going to show anomalous behavior. Okay, now let's understand what are the reasons for it. What is the reason for their different behavior? Why they behave differently from their respective group elements? Okay, now one thing common among all, they are from second period. One thing common among all is they are from second period. 2s2, 2p1, 2s2, 2p2, 2s2, 2p3, 2s2, 2p4, 2s2. Okay, I did it. I have missed fluorine here. Fluorine and neon. 2s2, 2p5, 2s2, 2p6. One thing common that they all are from second period, right? Yes. Acha. They all are from second period, so that's why they all are comparatively small than their respective group elements. Acha. One thing is that they are supposed to be small, but they are extremely small. We were expecting them to be small. For example, boron, after that aluminium. So of course, down the group size increases, so they should be small. But the problem is they are uh, extremely small. So one reason for their anomalous behavior is their small size. They all are very small as compared to their respective group elements. Second thing here is, as you will see, they all are from second period. Okay, so if they are from second period, right, if they are from second period, do you think they will have d orbital? Do you think 2D exists? Do you think that 2D exists? For 2D, n is equal to 2 and L is also equal to 2, which is not correct. N cannot be equal to L. N should be always more than L. So 2D does not exist. So what we can say from here, that they all of them, they do not have d orbital. The second reason is absence of d orbital. Absence of d orbital. Acha, now what is the consequence of absence of d orbital? What happens if they do not have d orbital? So they cannot extend their covalency. These elements here, these second period elements, cannot expand their covalency. What is the meaning of it? Boron only forms 3 bonds, but that is not the case with aluminium. Carbon only forms 4 bonds, but that is not the case with silicon. Nitrogen maximum 4, but phosphorus can expand their covalency up to 5. Oxygen forms only 2 bonds, but sulfur, as you know, oxygen can form only 2 bonds, but sulfur, the same group element, can expand their covalency up to 6. I hope you are understanding. These elements, their number of bonds formed by them is limited, but the elements from these groups, their respective groups, they can expand their covalency, they can form more number of bonds, and that because of d orbital. Okay, now let me explain this. Let me explain you this concept. For example, oxygen, 1s2, 2s2, 2p4, right? Oxygen forms 2 bonds. Why? Because it has only 2 unpaired electrons. Correct? Okay. Sulfur. Sulfur is, I'm just writing the outer configuration. 3s2, 3p4, and sulfur has 3d empty. Oxygen does not have, oxygen does not have empty d orbital. Oxygen does not have empty d orbital. Sulfur has d orbital. So what happens, if you will see, if we will unpaired all the electrons, 1, 2, 3, 4, 5, 6. Okay. So this one of this electron, I will write here 1, 2, 3, 4, 5, 6. So what we have done, we have shifted one electron here, we have shifted one electron here. Understood? Yes. So why this expansion has formed? Now sulfur has 6 unpaired electrons. It means it can form 6 covalent bonds. Oxygen has only 2 unpaired electrons. It means it can form only 2 bonds. And why this limitation for oxygen? Because it does not have d orbital. Okay. So absence of d orbital, these elements cannot expand their covalency. Okay. Now I hope you have understood. Third reason is that because they are small in size, so what happens? Because of less smaller size, their tendency to attract the electron becomes more. So let me explain you this. For example, one element is small in size, so it will be the nucleus will be closer to the nucleus. Nucleus will be closer to the electron. It means that electron can be easily attracted by the nucleus as compared to the element which is bigger in size. Okay, which is bigger and large in size. When it is large in size, the electron is far from the nucleus. When it is close in size, the electron is closer to the nucleus. Okay, so what happens, because of the small size, tendency of the atom to attract an electron increases. So third reason is high en. High en. Because of small size, these elements these elements becomes highly electronegative. These elements become highly electronegative. So these three are the reasons, these three are the main reason, these three are the main reason that these elements show anomalous behavior. And what are the anomalous behavior? What are the anomalous behavior? I will tell you. Anomalous behavior is their bonding is different. Bonding is different. Okay. For example, boron, it forms covalent compound. Boron forms covalent. Boron, aluminium, gallium, indium, and thallium. And thallium compounds are ionic. Fine. Okay. This is so anomalous behavior is their bonding will be different. Then covalency will be different. Number of bonds formed by them will be different. Okay. Fine. Okay, fine. So what I will do, I will just download here the NCRT, so that you will come to know that what you have to read from the NCRT, and we will see that all what are the anomalous behavior for each element. I have explained you the reason, what are the reasons they show different behavior. Now from the NCRT, I will tell you that what are those anomalous behavior. Okay, so this is the NCRT. Fine. And boron family. So let's read what are the anomalous behaviors shown by boron here. This group element shows a wide variation. Boron is a typical non-metal. First anomalous behavior. Okay. Boron is fairly rare element. Okay. Then here. Important trends and anomalous behavior of boron. What are the anomalous behaviors shown by boron? Okay. The certain compound, certain important trends can be observed in the chemical behavior of group 13. The trichloride, bromide, and iodide of all these elements being covalent in nature and hydrolyzed in water like this, except in boron, exist in aqueous medium. So, like this, you have to stick to the portion and you have to read. So, what is the exception? The trichloride, bromide, iodide of all these elements being covalent in nature and are hydrolyzed in water, and they give like this, except in boron, except in boron exist in aqueous medium. So what they have told, what is the anomalous behavior of, what is the anomalous behavior of boron, what is the anomalous behavior of boron? What they told, trichlorides, trichlorides, tribromides, triiodides of boron, aluminium, gallium, indium, and thallium of this, right? They are generally, they are generally covalent in nature. They are generally covalent in nature. First point, okay. And these halides, and these halides can be hydrolyzed. These halides can be hydrolyzed to give tetrahedral units like this. But who does not follow this? Who does not follow this? Exception is boron. Exception, boron. Who all does this? Aluminium, gallium, indium, thallium. But who does not follow this trend? That is boron. Okay, first anomalous behavior. So what we are doing here, what we are doing here, anomalous behavior of boron. Anomalous behavior of boron. So this is the first anomalous behavior. Okay. The monomeric trihalide being electron deficient are strong Lewis acid. Boron trifluorides easily react with Lewis base such that ammonia to complete octet around. So this is the next. The monomeric trihalide being electron deficient are strongly Lewis acid. Boron trifluorides easily react with Lewis base. Now let's see this. Next, the next anomalous behavior. The next anomalous behavior. The next anomalous behavior is trifluorides of boron. For example, BF3. Okay. So 1, 2, 3, 4, 5, 6. 6 electrons. Incomplete octet. Electron deficient. Correct? Incomplete octet, they are electron deficient. So BF3 electron deficient, they are called what? Lewis acid. Correct? So BF3 is a Lewis acid. And boron 1s2, 2s2, 2p1. One of the electron will excite here, here. एक, दो, तीन. It will always have incomplete p orbital. It will always have incomplete p orbital. So boron has incomplete p orbital. And ammonia, this is Lewis acid, right? This is Lewis base. Correct? Yes. So what happens? This electron, which is what? Lone pair, and it has empty p orbital. It will go this. What kind of bond is this? This is coordinate bond. This is coordinate bond. Contribution by only one, and sharing by both. Correct? So this is the another anomalous behavior shown by BF3. To overcome this electron deficiency, it forms a bond with ammonia. To overcome the electron deficiency, it forms the bond with ammonia. Correct? Yes. Now let's see the another anomalous behavior. It is due to the absence of d orbital. As I have told you, anomalous behavior is shown by the elements because they do not have d orbitals. It is due to the absence of d orbital that maximum covalency of B is 4. Since the d orbitals are available with aluminum and other element, they can expand their covalency beyond 4. Most of the other elements, halides, are dimerized through halogen bridging. The metal species completes its octet by accepting the electron. Okay, fine. So again, one more exception, one more the anomalous behavior of this is boron cannot expand its covalency beyond 4. Fine. Okay. Now let's see here. What is the question? Boron is unable to form BF63 minus. Why? Boron can maximum form. What is the thing for this? AlCl6 exists. Sorry. Why BF6 minus does not exist? Does not exist. Why? The reason is boron cannot expand its covalency beyond 4. Okay, fine. So whatever questions are given in the NCERT in text exercise, you follow that also. BF63 minus because it cannot expand its covalency. Okay, now fine. So these are the anomalous behavior. These are the anomalous behavior given by boron. Let's move Now next is carbon, anomalous behavior of carbon. Anomalous behavior of carbon. Carbon family, ionization energy, here. Reactivity towards halogen, important anomalous behavior of carbon, right? Like first member of the other groups, carbon also differs from the rest due to its smaller size, high En, higher ionization energy. What is the meaning of ionization energy? Energy required to take out the electron. When the element is very small, I'll show in the our board. When the element is very small, the valence electron is strongly connected to the nucleus. So removal of it becomes difficult and we have to provide larger energy. So that's why small size, high En, absence of d orbital and high ionization energy, these are the four reasons behind anomalous behavior of all the first group elements. In carbon, only SNP is present, so it can accommodate for only 4 electrons. So covalency is limited to 4, right? So what is the first anomalous behavior of carbon? Covalency is limited to 4. It cannot expand its covalency beyond 4. Okay, now next, carbon has also unique ability to form p-pi multiple bonds with itself and with the other atoms of small size and high En. Like this, heavier elements do not form p-pi bonds because their atomic orbitals are too large and diffused. So again, what is the next behavior? Carbon forms p-pi multiple bond, p-pi multiple bond with itself and with other elements which are small in size and which are highly electronegative, this behavior is not shown by this behavior is not shown by other elements of group 14. I will explain you why. C double bond C we know, C triple bond C we know. So one is sigma, one is pi. This is which pi? P pi. This is which pi? P pi. Correct. C double bond O, C double bond N. Right. This is also P pi. This is also P pi. Right. So what actually happens? What actually happens here? That if you will take silicon, germanium, tin and lead, they have large size orbital. Bonding becomes poor. Because bonding becomes weak due to poor overlapping. We know that covalent bond depends upon orbitals overlapping. If the overlapping is poor, the covalent bond will be weak. So they do not form multiple bonds. Why they do not form multiple bonds? Because the overlapping is not that effective. If the overlapping is not that effective, how the bond will be strong? So this is the anomalous behavior. Second, that carbon forms multiple bonds with itself and it also forms with the others. But these elements cannot show the double triple bonds because double triple bonds are very very weak here. Okay. Now next, what is the next anomalous behavior? Here, carbon atoms have the tendency to link with one another through covalent bonds to form chains and rings. This property is called catenation. Again, what is the property? Carbon atoms have the tendency to link with one another. Carbon atoms have the tendency to link with one another through covalent bonds to form chains and rings. This property is called catenation. Okay. So, next, what is anomalous behavior? The anomalous behavior is carbon has unique. Why we are calling it unique? Because no other elements of group 14 will show this behavior. Carbon has unique ability to form bonds with itself, to form bonds with itself, which is called catenation, which results into rings and chains, which results into rings and chain. This property is called this property is called catenation. Correct? This is the reason, that's why the whole organic chemistry is based on carbon. Carbon has the maximum number of compounds because they have the self-linking property. Carbon, 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 like that, they can form a chain of 100 carbon. So that's why there are maximum number of compounds which exist in nature of carbon, and that's why carbon chemistry is so vast and we study as separate as organic chemistry. Okay. And why, now the problem is, why only carbon shows catenation? Why not silicon? Why not germanium? Why not tin? Why not lead? So answer is, this is because carbon carbon bonds are very strong. First point. Down the group, the size increases and electronegativity decreases, thereby tendency to show catenation decreases. This can be clearly seen from the bond enthalpy. Okay, bond enthalpy. What is the order of catenation? So very important, whatever data is given in the NCERT, you have to know it, you have to stick with the portion, and whatever information is there in the NCERT, especially for inorganic, you have to read it very thoroughly and remember it. So who has the maximum catenation? Carbon maximum, silicon, then germanium, and then tin. So catenation order. Catenation tendency. Catenation tendency order. Carbon, silicon, germanium, and tin. And what is the reason for it? Carbon being smaller in size, carbon being smaller in size, carbon forms stronger bond. Carbon forms stronger bond. Carbon carbon bond is strongest as compared to other elements of this group, as compared to other elements of this group. Okay, fine. Now let's come to this table. Now let's come to this table. Carbon, carbon, silicon, silicon, germanium, tin and tin. So as we know, bond enthalpy is energy required to break a bond, right? Which bond requires the maximum energy to break the bond is carbon, 348. Carbon requires the maximum energy to break a bond. Stronger the bond, shorter the bond. So bond enthalpy order will be what? What is the bond enthalpy order? What is the bond enthalpy order? Correct. Carbon, carbon, silicon, silicon, germanium, germanium, tin and tin. You do not need to remember the what is the bond energy values, just you need to remember the order, because what they have mentioned there, general order, like who is more, who is less. No need to remember the values. Okay, so this is the anomalous behavior shown by carbon. This is the anomalous behavior shown by carbon. Due to property of catenation and pp bond formation, carbon is able to show allotropic forms. So again, okay, now the thing is, due to catenation and tendency to form pp bond, tendency to form pp bond, carbon can show allotropy. What is allotropy? What is allotropy? Allotropy is that tendency to exist in more than one forms. For example, carbon has, what are the more than one forms of carbon? Graphite, diamond, fullerene, coal. These are the different forms where the core element is carbon, but their chemical behavior, physical behavior is completely different. Okay. Now, what are the allotropes of carbon? Diamond. Okay. What you will remember in this, in the allotropes of carbon? Diamond. What they can ask you in the exam, what is the hybridization of carbon in diamond? So it is sp3. For graphite, 1 2 3, it is sp2. Fine. So this diamond, it is sp3, it is also a form of carbon. Graphite, that is also a form of carbon, allotrope of carbon. Hybridization is sp2. Diamond is a 3D packed cage like structure. Graphite is layered structure. Why graphite is slippery in nature? You have used pencils. The pencils, we have the lead. In that lead, that not sorry, in that pencil there's a graphite. And why, if you have touched that lead, the pencil lid of the pencil is made up of graphite. If you have touched that, that is slippery. Slippery means what? Like this, it slips. And why it slips? One layer and the another layer, one layer and the another layer, they are formed by weak van der Waals forces. These two bonds, bond between this and this, can be broken easily. So when we broke it easily, when we do like this, we are applied the force, so it slips like this. So that's why graphite, one layer another layer, slips like this. Okay, now next, this is the allotropes. What you have to remember in the allotropes? Diamond, allotropes of carbon mein, what you have to remember? Allotropes of carbon. Okay, the first one is diamond. The first one is diamond, graphite, diamond, graphite, fullerene. Fine. Diamond, the carbon is sp3 hybridized. Graphite, the carbon is sp2 hybridized. Okay, diamond is the hardest element known on the earth. Hardest element known on the earth. Carbon is slippery in nature. This is slippery in nature. It is slippery in nature and it exists in the form of layers. Exists in the form of layers. They can ask you between two layers, what are the forces? Between two forces, between two layers, there is van der Waals force of attraction. Van der Waals force of attraction. There is van der Waals force of attraction between these two layers. This is van der Waals, which is very weak. Fine. Here, allotropes of carbon. There are two allotropes, crystalline and amorphous. Diamond, graphite, fullerene. They are types of crystalline allotropes. Amorphous, coke, charcoal, coal, sea lamp black. These are the amorphous allotropes. Acha. Then diamond, each carbon, for diamond the carbon is sp3. For graphite the carbon is sp2. Each carbon atom is bonded with 4 other carbon atoms. Hybridization sp3, tetrahedral structure. sp3 means, what is the structure? What is the structure? sp3 means tetrahedral structure. Insulator due to the absence of free electrons. As you know, carbon is a non-metal. Why it conducts and diamond does not? Diamond is an insulator. Diamond is a insulator. It does not conduct electricity. But graphite conducts. If you will see, carbon has 4 valence electron, but here it is using only 3. So if it is using only 3, the 4th electron is free, which can move from here to here and to here to there, right? Which can conduct. But this cannot conduct because all 4 are being used. What is the criteria for compound to be conductor? They should have any charge with it, either in the form of electrons or in the form of free ions. So graphite conducts because it has 1 free electron. And highest melting point, giant molecule, carbon carbon bond length is 1.5. Carbon carbon bond length between in this is 1.54 angstrom, and for diamond this is 1 point, carbon carbon bond length is 1.41 angstrom. 1.41 angstrom. Conductor due to the presence of delocalized electron, soft due to the presence of weak van der Waals forces. The whose bond length is more, graphite or diamond? Bond length. Whose bond length is more, graphite or diamond? Bond length. Whose bond strength is more? Whose bond strength is more, graphite over diamond? We are not talking about the overall molecule. We are just told carbon carbon bond length is stronger in graphite and it is weaker in diamond. It is weaker in diamond. Now fullerene. What is about fullerene? Fullerene is C60, C70, C60 and C70. These are the common forms of fullerene. C60 is also known as Buckminster fullerene. Okay. There are 32 rings, 50 pentagon. Pentagon means like this. 20 hexagon. Hexagon means like this. So if you will see here, this is pentagon. These are 12. This is hexagon. This is also pentagon. Just a second. This is hexagon. Uh, this one is hexagon, and hexagon is 20. Okay, so this information better you remember. There are 50 12 pentagons, and there are 20 hexagons. Okay, each carbon is bonded with three other carbon, sigma and double bond. sp2 hybridized and aromatic in nature. Fullerene is aromatic in nature. Okay, and the carbon here is sp2 hybridized. It is purest allotrope of carbon, and this is the purest allotrope of carbon. Fine. So this is about the anomalous behavior of carbon. This we have done, the anomalous behavior of carbon. Correct. Graphite, this one. This is pentagon, this is hexagon. Okay, then fine. Now quickly we will see the anomalous behavior of oxygen, nitrogen, fluorine and neon. Anomalous behavior of nitrogen. So this we will do. Let me drink little water. Okay, so now we will do anomalous behavior of nitrogen. What are the anomalous behavior shown by nitrogen? Okay, nitrogen differs from the rest of the members of this group due to its small size, again high En, high ionization energy and non absence of d orbital. Nitrogen has unique ability to form p pi multiple bonds. So now next we are doing anomalous behavior of nitrogen. Now next we are doing anomalous behavior of nitrogen. Anomalous behavior of nitrogen. Next we are doing anomalous behavior of nitrogen. So what is the first anomalous behavior? That it can form p pi multiple bond. It can form p pi multiple bond. Next is with itself and with the other elements. Heavier elements do not form, again the same concept, again, that they do not form p pi p pi. The heavier elements cannot form p pi p pi multiple bonds, because if they will form, that will be poor and they will not exist. Okay, again the reason: nitrogen exists as a diatomic molecule with triple bond, one s and 2p between two atoms. Consequently, its bond enthalpy is very high. On the contrary, phosphorus, arsenic, and antimony form single bonds as pp, arsenic, and antimony, while bismuth forms metallic bonds in elemental state. So, what is the next behavior? Multiple bonds with itself, and with other elements, and with the other elements. It can form p pi p pi multiple bonds with itself and with the other element. Nitrogen forms triple bond with itself. Nitrogen forms triple bond with itself, N triple bond N, right? Where is phosphorus, arsenic, antimony? Where is phosphorus, arsenic, antimony, and bismuth? They form single bond. They exist as pp, arsenic, antimony, and antimony, right? They Bismuth forms metallic bond, because bismuth is metal. It does not form the covalent bond. It forms metallic bond. So nitrogen behavior is different, metallic bond. And because N exists as this, the bond enthalpy or bond energy of N2 is very high. Of N2 is very high. Then yes, however, the single NN bond is weaker than the single PP bond. Just focus here, whatever the statements, again I am telling you, whatever the statements which are given in the NCERT, that is very important. In the exam, they can ask you directly questions from these statements. So what they have told here, N double bond N triple bond N is very strong as compared to other. But when they talk about N single bond N and P single bond P, then N single bond N is weaker. Okay, so its bond enthalpy is very on the fine. The single NN bond is weaker than the single PP bond because of high interelectronic repulsion of the non-bonding electrons owing to small bond length. As a result, the catenation tendency is weaker in nitrogen. So what they have told here, let me explain. What they have told here, N triple bond N is stronger, right? But when they talk about N single bond N single bond N is very, or better we will write weak. N single bond N is weak. Why they are weak? N single bond N, lone pair and lone pair. Neutral N will always have one lone pair. So there will be repulsion between it, right? So because of electronic repulsion, because of electronic repulsion between lone pair on nitrogen, the bond becomes weak, right? The bond becomes weak. The bond becomes weak. So they can ask you in the exam, why the they can ask you N single bond N and P single bond P, which is stronger? Which is stronger? The answer is N triple single bond N is weaker than P single bond P. What is the reason? Because N is small in size, the lone pairs are very close to each other, and uh, P The size is large. Okay, so repulsion is less. This repulsion, this electronic repulsion is less. Here the repulsion is more. Here the repulsion is more. Okay, fine. So better you remember this. Hmm. They cannot form d pi p pi bond. Okay. So N cannot form d pi p pi bonds, and its covalency is up to 4. N, its covalency, what is the covalency for nitrogen? Nitrogen covalency is covalency for nitrogen is only 4. Correct. Covalency for nitrogen is only 4, and it does not form it does not form p pi d pi bond. To form p pi d pi bond, it should have d orbital, and nitrogen does not have d orbital. ठीक है? Okay, so this is the anomalous behavior of nitrogen we have done. Because it is mentioned in the portion, it is very important to read it thoroughly. Now let's see anomalous behavior of O2. Now let's see anomalous behavior of O2. Now let's see anomalous behavior of O2. Group 16 elements, physical property, dioxygen, simple oxides, preparation, ozone, here. Anomalous behavior of oxygen. So our next topic is anomalous behavior of oxygen. Anomalous behavior of oxygen. The anomalous behavior of oxygen, let me write it the next topic. Anomalous behavior of oxygen. What are the anomalous behavior of oxygen? Same, the reason is same. The absence of one typical example of effect of small size, that hydrogen bonding in H2O. We know this, that water, oxygen, it can form H bond. Strong. Let me show this. Wait. O, H and H. Partial positive, partial negative. Partial negative. So that oxygen can form stronger H bond, and no other elements of this group shows a stronger H. They do not show H bonding. Oxygen, because of its small size, high En, it shows a stronger H bond. The absence of d orbital in oxygen limits covalency up to 4 and rarely exceeds 2. On the other hand, in case of other elements, again the same, covalency for covalency for oxygen is up to 2, and hardly it exceeds 2. Okay, so this is the anomalous behavior of oxygen. Again, the reason is same for all: small size, high En, absence of d orbital. It's okay. Now we will see the anomalous behavior of fluorine. The anomalous behavior of fluorine. What is the anomalous behavior of fluorine? Let's see here. Reactivity towards metal, halogen. Wait. Physical property. Here. So, what is the anomalous behavior of fluorine? The smaller enthalpy F2 compared to Cl2. Again, this is also very important, right? What is the trend? Chlorine, chlorine, bromine, iodine. Where is X bond in the chlorine towards the respected? This anomaly is relatively larger electron. Okay, fine. So, what they are telling you is FF bond, FF bond is supposed to be stronger. FF bond is supposed to be stronger. FF bond is supposed to be stronger. Okay, but F F 2p and 2p, 1 2 3 4 5 6, 1 2 3 4 5 6. This, the electronic repulsion is more. The electronic repulsion is more. The electronic repulsion is more, right? Which makes the molecule weaker. Chlorine was supposed to be stronger. Sorry, this chlorine bond supposed to be weaker because there is a 3p bond, right? Fluorine bond is supposed to be stronger because small orbitals are overlapping. But shockingly, chlorine bond is better. Bromine bond, and then weakest is iodine, and between chlorine and fluorine, this is the bond strength. Bond strength is highest for chlorine and as compared to fluorine, and this is the bond strength order. Whatever order is given in the NCERT, you have to make sure that you remember that trends, you remember that sequence. Okay, so here we have finished mostly the anomalous behavior. One part of our portion is over. Anomalous behavior of uh, first member. Anomalous behavior of the first member. Let me quickly summarize this. Boron, carbon, nitrogen, oxygen, fluorine, we have done. Boron anomalous behavior, it forms bond with the Lewis base. Boron covalency is up to 3. It can up to 4. It cannot the trihalides, triiodides, trichlorides of boron cannot hydrolyze. Carbon can form allotropes. Carbon can show catenation. Carbon can show multiple p pi bonds with itself with the other elements. And for nitrogen, it can form triple bond with itself, but the other elements of its groups cannot show. oxygen, it shows H bonding. No other element in oxygen family can show H bonding. So these are the anomalous properties of these elements. And in the last, fluorine and chlorine bond. Fluorine is a small in size, so electronic repulsion is more, the bond is weak. After that, what are the reasons for these elements shows this anomalous behavior? Small size, high En, and absence of d orbital and high ionization enthalpy. Now let's go back to the next topic, chemical and physical behavior of these groups. What is the trends across the period and across the group? So quickly revise the important topics. Just a second. Okay, let's come here. This is a very important topic, inert pair effect. Okay, so what is inert pair effect? Let me explain, then we will come here. What actually happens? You have a atom, then electron is present here, right? Then you have another atom. This I am explaining what concept inert pair effect. Okay, what I am explaining, inert pair effect. Okay, fine. Let's come to this. Let's say this is electron A and this is electron B. If I will ask you which electron is feeling, a second, wait. Electron A and electron B. Correct? So if the question is which electron is feeling the more nuclear charge, the question is which electron is feeling the more nuclear charge, A or B? Who is feeling the more nuclear charge? So if you will see, this is the nucleus, and these the this here the shielding is poor or better? Shielding of this shell is poor. This is poor shielding. Okay, and this is, if it, this will block it, the nuclear charge will block. The shielding of this is very good shielding, best shielding, or we can say that better shielding. We can say that better shielding. Fine, this is poor shielding, this is better shielding. Which electron will feel more charge, EA or EB? Which electron will feel more charge, electron A, electron B? So the answer is, this shell will not be able to, this shell will not be able to shield properly, right? So Z effective is more for EA than Z effective for EB. It means that EB electron will feel less charge, EA electron will feel more charge. Acha, now tell me which electron is difficult to remove, because EA is more attracted to the nucleus. EA is more attracted to the nucleus. EA is more attracted to the nucleus, hence difficult to remove. Hence difficult to remove. Correct? Hence very difficult to remove. And EB is less attracted. EB is less less attracted to the nucleus. EB is less attracted to the nucleus, hence difficult to remove. Hence difficult to remove. Correct? This is the shielding. Shielding is reverse of Z effective. Shielding is reverse of shielding is reverse of Z effective. I hope you have understood. Better the shielding, the outer electron will feel less nuclear charge. Okay, this is a shielding effect. For example, I am here and this is a shielding. If the shield will be better, the person next to me will not be able to see me. And if the shield is thick, thin, then the person next to me can hear me, can see me. It means that I can influence. So nucleus can influence the electron if the shielding is poor, and if shielding is best, nucleus have no influence over the electron. So I hope you have understood the shielding. Shielding is reverse of Z effective. Now what happens? What is the shielding order? What is the shielding effect? Shielding is also called screening effect. It is also called screening effect. Whose screening is best? S, P, D and F. They have the S has the best shielding effect, then P, then D and then F, right? So better shielding, S will show the better shielding than P, then D and F, right? Okay, now what happens if you will see, let's say boron family. Boron electron is 2s2, 2p1. Who is shielding this valence electron? Who is shielding these valence electron to 1s2? And 1s2 has best shielding. 1s2 has best shielding. If the shielding is best, Z effective is more or less. Z effective is less. If the shielding is best, Z effective is less. Z effective is less means these electrons can be removed easily. Can be removed easily. If they can be removed easily, so boron can show +3, right? But if we will come to thallium, boron, aluminium, gallium, indium and thallium, right? 6s2, 6p1. Before this, there will be F orbital, right? F has poor shielding. F shielding is poor. F has poor shielding. If shielding is poor, Z effective will be less. Sorry, Z effective will be more. These electrons, S2, these electrons strongly attracted to the nucleus, and they will be tough to remove. They are going to be tough to remove, hence they will only remove this. So thallium will only show +1, right? Why? Because the 6s2 electrons has become inert. Ns2 electron has become inert. Has become inert. Okay, if the electrons has become inert, it is tough to remove, hence the element can only take out the electron which is present in the p orbital. Okay, so this is called inert pair effect. Fine. If I will tell you in one statement, Ns electrons in p orbital becomes inert because of the poor shielding of F and D. When they become inert, it becomes difficult to remove it. Hence, this is called inert pair effect. What is the application of it? What is the application of it? As we move down the group, as we move down the group, as we move down the group, stability of, as we move down the group, stability of higher oxidation number increases, higher oxidation number decreases, and stability of, and stability of lower oxidation number increases and stability of lower oxidation number increases. Okay. It means boron, aluminium, gallium, indium, and thallium. Boron will show +3, thallium is happy in +1. As we go down the group, lower oxidation number, lower oxidation number stability increases. As for this, higher oxidation number stability is more. Correct? So what are the for same for carbon family? Carbon, silicon, germanium, tin, and lead. Correct? Right? +2, and for lead, carbon shows +4 and lead +2. Fine. Same. So boron family, carbon family, as we go lower in the periodic table, higher oxidation number becomes less stable, lower oxidation number becomes more stable. This is the inert pair effect. Now quickly see here, for boron +3, aluminium +3, for gallium +3 is more stable than +1, for indium. So in the they will not even show +1. Boron and aluminium will not even show +1. They will show, but +3 is still more stable for gallium and indium. What you will remember that thallium ke liye, for thallium +1 is more stable. Carbon +4, silicon +4, they will not even show +2. Germanium +4 is more stable. Tin +4 is more stable. Lead +4 is more stable. Sorry, germanium +4 is more stable. Tin +4 is more stable. Lead +2 is more stable. So how, what you will remember, group number 13 boron family, thallium +1 is more stable. For group 14, lead +2 will be more stable. For group 15, arsenic +5, bismuth +5, arsenic, antimony +5, bismuth +3. So let me tell you quickly, carbon, boron, and nitrogen, they, for these elements in this family, एक second, boron, carbon, nitrogen, boron, carbon, nitrogen, boron, carbon, nitrogen, for this family, only for thallium +1 is more stable. Only for thallium +1 is more stable. For carbon family, only for lead +2 is more stable, and for only bismuth, only +1 is more stable. Right? Fine. Now, what are the applications of this effect? What are the applications? If you will see PbCl2, they can ask you PbCl2 +2, PbCl4 +4. Which one is more stable? So, stability is more for PbCl2. Right? Again, GaCl3 and TlCl3. TlCl3 and GaCl3. Ga +3 and +3. We know that for gallium +3 is more stable than +1, and for thallium +1 is more stable. So this is the correct one, right? Thallium does not exist. Thallium iodide does not exist. So what is the reason for this? Thallium iodide does not exist. What could be the reason for this? The reason for is thallium is not stable in +3 state. Among pentahalide, bismuth only shows this. For bismuth, if it will show pentahalide +5 and BiF3 +3. So, kaun sa which one is more stable? This one is more stable because for bismuth +5 and bismuth +3 is more stable. Correct? Okay. So, now TiCl is more stable again, +3 +1 is more stable again. For tin, it is +4 is more stable than lead +4. PbF4, BbF4 exists, but PbR4 and PI4 does not exist because they are large in size. Fine. Acha. One more concept can be asked in this. They can ask you PbI2 and PbI4, which works as a stronger, which works as stronger oxidizing agent, right? So what is the meaning of oxidizing agent? The one who self reduces itself. The one who self reduces itself. The one who self reduces itself, plus 2, and here it is plus 4, right? So who will reduce itself? Plus 4, no, stronger oxidizing agent, not stronger oxidizing agent, stronger reducing agent, which is a stronger, which works as stronger reducing agent, which works as stronger reducing agent, which works as stronger reducing agent. Which one will work as a stronger reducing agent? So what is the answer for this? Which one will work as a stronger reducing agent? Stronger reducing means the one who will the one who will reduce itself. Plus 4 to plus 2. What is this? Self reduction, right? This self reduction from plus 4 say plus 2. So it will who will work? This is working as a stronger oxidizing agent. This is working as a stronger oxidizing agent. Correct? So like that also, that for example, if they will ask you SNI4, PBI4, who will work as stronger oxidizing, stronger oxidizing agent, yes, which is a stronger oxidizing agent. So answer is this, because tin will not go from plus 4 say plus 2. Okay, so this was a very important concept of inert pair effect. Let's see some questions. I have brought some PYQs. So let's see whatever we have discussed till now. uh, can we solve some questions from this? So this is the boron family. See here, boron family. So as I have told you that these concepts are very important, and always when we are preparing for a topic, we cannot skip PYQs. So just take 2 minutes and I will discuss all three questions. So tell me the answer for this. Taking stability, let's discuss this question. Taking stability as a factor, which one of the following represents correct relationship? So what we know, thallium plus 1 is more stable than plus 3. This is correct. Thallium plus 3, no. Aluminium plus 1. Aluminium does not show plus 1. Indium plus 3 over plus 1. Uh, Fine. So plus 3 over plus 1. So what is the, which one is the following represents correct relationship? So what is the answer? Definitely the first one is the correct answer. Boron, aluminium, gallium, indium, thallium. So for thallium, plus 1 is more stable than plus 3. So correct answer for this is question number 1. 2023 they have asked this question. Okay. Now which is, again, see, I have told you they will ask you directly from the NCERT, which one of the following element is unable to form Mf63 minus? So who is unable to form Mf63 minus? Answer is boron. Boron cannot expand its covalency beyond 4. So this is the correct answer, direct from the NCERT in text question. Okay. Now again, see, 2015 the same inert pair effect, the stability of plus 1. So plus 1 stability is highest for thallium, indium, gallium, aluminium. So correct answer is C for this. Okay, here question number 15. Again, this is based on the inert pair effect. Question number 15, it is based on the inert pair effect. It is because of the inability of ns2 electrons. SN4 is reducing. What is the meaning of reduction? It will reduce itself. So plus 4 and plus 2 is more stable. SN4 is reducing. It is not reducing, right? Because if it will reduce, it will go plus 4 to plus 2. But for SN, what is more stable? For SN plus 4 and SN plus 2, which one is more stable? For SN plus 4, SN plus 2, which one is more stable? The stable one is SN4. So it cannot be reducing. It cannot, it cannot be reducing. Correct? It cannot be reducing first. Then we have Then we have SN2 plus is reducing while PbO4 is oxidizing. Is reducing SN2 plus and PbO both. SN4 plus oxidizing while this is correct. Okay. So SN2 plus is oxidizing. What does it mean? That Sn plus 2 can oxidize to Sn plus 4. That is correct. Right? Pb4 plus can reduce to Pb2 plus. This is also correct. So Pb, this is reducing and it is oxidizing. Correct. The correct answer, basically the concept here is for Sn plus 4 is more stable than Sn plus 2. Lead plus 4 is more stable than plus 2. Plus 2 is more stable than plus 4. So based on this, this one is uh, this is oxidizing, this is reducing in nature. Okay. Now let's revise the other topics. This is inert pair effect is over. Okay. Now let's start from each family. So now we are starting from boron family, right? Okay. The boron is a typical non-metal. In boron family, boron, aluminium, gallium, indium, thallium. It is a typical non-metal. It is a typical non-metal. Aluminium is a metal. It is a metal. but shows many chemical similarities to boron. Gallium, indium, and thalliums are exclusively metallic. So these are metallic in nature. Now we are taking a group one by one. So now we have started with boron family. Okay, physical behavior, because it was mentioned in the portion that we have to read physical and chemical behavior, right? Their trends we have to do. So boron is non-metallic. It is extremely hard. This is very important. Boron being very small element, how it can be so hard, and why the metal melting point of boron is very high. Boron is non-metallic. It is extremely hard and black colored solid. Boron is extremely hard. Boron is extremely hard and boron is extremely hard and black colored solid and black colored solid. It exists in many allotropic forms. Boron has many allotropic forms. Due to very strong crystalline lattice, boron has unusually high melting point. Again, very focus here. Boron has exceptionally high melting point. Boron has exceptionally high melting point. Boron has exceptionally high melting point, right? Acha. Rest of the members are soft metals with low melting point and high electrical conductivity. Gallium is the metal which can be gallium with low melting point can exist in a liquid state during summer. Its boiling point makes it useful material for measuring the high temperature. Very important. These statements I have picked from the NCERT directly. So they can ask you what is the use of gallium. Gallium with low melting point can exist in liquid state. Its high boiling point makes it a useful. Its high boiling point. Melting point is very less. For gallium, melting point is very, very less, but gallium boiling point is very, very high. So its high boiling point makes it useful material for measuring high temperature. For example, we cannot take any metal to measure the high temperature. Let's say the temperature is 2000 Kelvin. If the metal melt before 2000, then how it can measure? So gallium can measure the temperature up to 2676. So that's why gallium is used as instrument to measure the temperature. Density of elements increases down the group from boron to thallium. Density increases boron to thallium. Density increases from boron to thallium. Now let's next is element oxidation number. This I have told you, boron has highest stability for +3 and thallium is highest stability for +1. This we have discussed already according to the inert pair effect. Okay. Then chemical behavior. Till now for boron family we have discussed the physical behavior. Now we are discussing the chemical behavior. What is the chemical behavior? Reactivity towards air. Boron is unreactive in crystalline form because it is very solid. The melting point is very high. If it will be that solid, how it can react? Aluminium forms a very thin oxide layer on the surface while protects metal from the further attack. Aluminium does not get rusted faster because it will cover itself with white layer, and that white layer is aluminium oxide that is coming from oxygen. Okay, so aluminium forms a very thin oxide layer on the surface which protects the metal from further attack. Amorphous boron and aluminium metal on heating in air forms B2O3 and Al2O3. So boron forms B2O3 and aluminium Al2O3 respectively. With dinitrogen at high temperature they form nitrides. Boron plus N2, it form Bn, right? Aluminium plus N2, they will form like this. So they will, with nitrogen they will form dinitride. The nature of these oxides varies down the group. Okay, let me explain you this nature of oxides. Nature of oxides. So oxides are basically three types. So oxides are basically of three types. So what are the three types? Covalent, amorphous and covalent. Sorry. Oxides are amorphous, acidic, right? Acidic. Oxides are acidic, basic, amorphous, and neutral. And neutral. Oxides are acidic, basic, amorphous, and neutral. What are the basic acidic oxide? So, non-metal oxides, non-metal oxides are non-metal oxides are acidic, non-metal oxides are acidic, metal oxides are basic. The one which can behave as both, the one which can behave as both, they will work as amorphous. Both means acidic and basic, both acidic and basic, right? Neutral, no behavior, neither acidic, neither acidic nor basic, right? Acha, acidity of oxides is directly proportional to positive charge, is directly proportional to electronegativity, is directly proportional to oxidation number, right? Is directly proportional to, sometimes not always, number of oxygen, number of oxygen atoms. For example, CO2 and carbon monoxide. Carbon monoxide, which one is more acidic? This is more acidic. Okay, fine. Basic, sodium oxide, Na2O2. Metal oxides, basic. Metals oxide, basic. Amorphous, which can work as both. Very famous example, aluminium oxide, zinc oxide. Neutral, there is only two neutral, carbon monoxide, this laughing gas, and NO. These are the three only examples of neutral oxides. So, what are the nature of the oxides here? Let's do. What are the nature of the oxides? Okay. So, what are the nature of the oxides? Here. The nature of these oxides, boron trioxide is acidic. Please, it is very important. You have to remember this B2O3 because it is non-metal. Boron is non-metal. So, this is highly acidic. Aluminium and gallium. This is amphoteric. This is amphoteric. Indium and thallium. These are basic oxides. So remember this, okay? Now, carbon family. Before starting this carbon family, just we will take a break of 5 minutes. I'll come back again. Then we will go to carbon, nitrogen, oxygen, and halogens, and then noble gas. So just 5 minutes break, and then we will come back to here again doing carbon family. Okay, so we will start with carbon family. Now, carbon and silicon are non-metals. Carbon, silicon, germanium, tin and lead. Carbon and silicon, these are non-metal. Carbon and silicon, these are non-metals. Germanium is metallic. Germanium is metallic, and tin and lead, these are soft metal. Okay. What are the characteristics? All 14th group elements are solid. They have higher melting point and boiling point than group 13 elements. Reaction with O2. All elements when heated with O2 form two types of oxide, MO and MO2. SiO only exists at high temperature. Carbon, silicon, germanium do not react with water. With the water, they do not react. Silicon decomposes steam to form dioxide and H2 gas. So remember this reaction. Silicon, sorry, tin, carbon, silicon, germanium. Carbon, silicon and germanium do not react with water. Carbon, silicon, germanium do not react with water. Correct? Tin decomposes steam. What is the meaning of steam? Steam means hot water. Steam, with steam, it reacts to give SnO2 and H2. So, tin decomposes steam, means hot water, and releases H2. Okay, fine. Now, lead is unaffected by H2O due to the formation of protection layer. Lead again do not react. Lead do not react with water. Okay, fine. So, lead do not react with water due to formation of protective layer formation. Okay, on itself. So who does not react with water? Lead does not react with water. Carbon, silicon, germanium does not react with water. Only tin decomposes steam into SnO2 and H2. Now, next, catenation property. Carbon, this we have done already in the anomalous behavior. Carbon has maximum tendency of catenation due to the formation of strong carbon-carbon bond. On moving down the group, tendency of catenation decreases due to increase in size. Lead does not show catenation. Lead does not show catenation at all. Carbon, silicon, germanium, carbon, silicon, germanium, and tin, lead does not show catenation. Tendency of self-linking property is called catenation. Now, next is our nitrogen family. Nitrogen, phosphorus, non-metals, arsenic, antimony, metalloids, bismuth, and bismuth is a metal. Now, next, okay, these are also called pnictogen. Nitrogen family is also called pnictogen. Nitrogen family is also known as pnictogen. Nitrogen family is also known as pnictogen. The first element is nitrogen. The first element, nitrogen, is a gas. The first element, nitrogen, is a gas. Nitrogen is a gas. The second member, phosphorus, is a soft waxy solid. Phosphorus is a soft waxy solid, however can pass readily into vapor state. The remaining elements are solid. These are the hard and possess metallic luster. Why? N2 is inert at room temperature, but phosphorus is highly reactive. Due to larger bond energy of N2 molecule, it is inert at room temperature, but P4 due to great angular strain is highly unstable and reactive. N2, there is a very strong bond which is tough to break, hence it is very less reactive. P4, if you will see, P4 is in the form of kite. Okay, so this is highly strained. This is highly strained. If it is highly strained, it will become highly unstable. Even at room temperature, its slow combustion takes place when exposed in air. That's why it glows in dark. Phosphorus glows in dark because phosphorus reacts with oxygen to form P4O10. Okay, because of this formation of P4 to O10, phosphorus glows in dark. After that, we have anomalous behavior of nitrogen. This we have discussed already. Nitrogen forms p pi bond, small size, high En, ease of formation of multiple bonds. Then we have atomic radii, very important: nitrogen, phosphorus, arsenic, antimony, bismuth. So no exception. Whenever you are doing these topics in the notebook, you can mention there is no exception here, right? So there is no exception. There is no exception here. Down the group size increases. Down the group size increases, so size is increasing, no exception for this. Ionization energy, down the group size increases, so down the group it should. Ionization energy, down the group size down the group size increases, ionization energy should decrease. So they are following the normal trend. Again, no exception here. Okay, no exception. Down the group ionization energy decreases. Correct. Catenation, tendency of self linkage is catenation. In general, it decreases down the group due to decrease of small of atom. In group 15, order of catenation follows like this. Who shows the catenation? Nitrogen does not show catenation because N bond is weaker. In the exam, they can ask you why nitrogen being small in size, but still it does not show catenation, but phosphorus does. So answer is nitrogen and phosphorus. This phosphorus bond is stronger because nitrogen being small in size, the repulsion between the lone pairs is more, and here the repulsion between phosphorus elements is less because size is more. The lighter element N, P and arsenic exhibit the property of catenation, but this property is much less than group 14. Group 14, carbon. Carbon family shows more catenation than nitrogen family. After that, oxidation number. The common oxidation state of these elements is -3, +3 and +5. The common oxidation number for these elements is -3, +3 and +5. Okay, next, oxidation number. The tendency to exhibit -3 oxidation state decreases down the group up. This you know, lower oxidation number. This is lower oxidation number. So down the group, the stability of lower oxidation number decreases, and that of +5 decreases on moving down the group from N to B. The tendency, the stability of +3. Now we have two oxidation number, -3, +3 and +5. Okay, so between these two, the lower oxidation number +3 stability increases down the group. +3 in stability increases down the group, and +5 stability decreases down the group. Okay, fine. For example, if you have nitrogen, phosphorus, arsenic, antimony, bismuth. Bismuth will show BiF3. It will not show BiF5 because here it is +5 and here it is +3. So which is better? +3 is better. Okay, fine. The stability of plus 3 oxidation number increases and plus 5 decreases from N to bismuth due to inert pair defect. In case of nitrogen, all oxidation number plus 1 to plus 4 tend to disproportionate in acid solution. Very important. What is the disproportionation? What is the meaning of disproportionation? Same element, same element gets oxidized and the same element get reduced, and the same element gets reduced. Okay, so here plus 3 plus 5 plus 2, so plus 3 to plus 2 reduction, plus 3 to plus 5 oxidation. Which oxidation number show disproportionation? Which oxidation number will show disproportionation? Lowest oxidation number cannot show, highest oxidation number cannot show. Minus 3 to plus 5. So plus 5 cannot show, minus 3, but intermediate. So what they have mentioned from plus 1 to plus 4. Plus 1 to plus 4. Always remember the oxidation number which is lying between the maximum value to minimum value can disproportionate. Can disproportionate, right? Plus 1 to plus 4, they can disproportionate. This is the example. Now, in case of phosphorus, nearly all intermediate oxidation state disproportionate into plus 5 and plus 3 in alkali and acid. In case of phosphorus, for nitrogen, plus 1 to plus 4 oxidation number, plus 1 to plus 4 oxidation number, this is going to show disproportionation. Then for phosphorus, plus 5 to minus 3, between this they will show disproportionation. Okay. Then oxidation state shown by the nitrogen. Oxidation state shown by the nitrogen, 0. Nitrogen shows all kind of oxidation number, plus 2, plus 3, plus 4, plus 5, minus 3, minus 2, minus 1, and even it shows fractional. So they can ask you in the exam the question that this is the element, what is the oxidation number here? So it is plus minus 1 by 3, right? So next is oxides. So what type of oxides they form? They form E2O3 and E2O5. So here it is plus 3 and here it is plus 5. Which oxidation number, which oxide is more acidic? So what is the answer here? Which oxide is more acidic? Which oxide is more acidic? The answer is E2O5 is more acidic than E2O3, right? Acidic nature is directly proportional to An, it is directly proportional to oxidation number, right? So N2O3, N2O5. As nitrogen, phosphorus, arsenic, antimony, and bismuth. As we go down the group, non-metallic character. As we go down the group, non-metallic character decreases. As we go down the group, non-metallic character decreases. Hence, acidity of oxide. Hence, acidity of oxides decreases, right? So this is the order. Which one is highly acidic? Correct. Stability of oxides of higher oxidation number decreases down the group. Down the group, higher oxides does not exist. Then N2O5 is quite stable, okay, while B2O5. So higher oxides, stability of higher oxides is less as we go down the group. right? Due to inert pair effect. Because, for example, if you will take N2O5 plus 3, bismuth plus 5 plus 5. Higher oxidation number is more stable for smaller element. So plus 5 is for bismuth plus 5. So this is more stable. Okay, fine. Besides all these three type of oxides, nitrogen forms, uh, these are neutral. So acidic, basic, neutral, and amphoteric, N2O and NO, these are the neutral oxides, right? The reluctance of phosphorus, arsenic, antimony, bismuth to enter into p-pi multiple bonds leads to cage structure for those oxides. They exist as dimer, right? Now, let's move to the hydrides, the very important part here, the hydrides. Okay, so let's start from this, and this is very important again. This is very important. Let me explain this to you. And see here, hydrides. Hydrides of group, hydrides of group 15. Hydrides of group 15. Ammonia, phosphine, NH3, PH3, nitrogen, phosphorus, arsenic, antimony, and bismuth. Okay, fine. First, bond angle. They all are, they all should be sp3 hybridized. They all should be sp3 hybridized, but nitrogen only is sp3. Rest of them, these elements, these elements do not use, these elements do not use these elements do not use hybridized orbital. These elements do not use hybridized orbitals. They use pure orbitals, right? So in this case, there is no hybridization. So for them, what is the angle? 104 point something. Here the bond angle is 104. But this, the bond angle is, here, the bond angle is nearly 90 degree. The bond angle is nearly 90 degree. So as we go down the group, as we go down the group, bond angle decreases. Bond angle decreases, right? So what is the order for the bond angle? Ammonia maximum, ammonia, phosphine, antimony, nitrogen, phosphorus, arsenic, nitrogen, phosphorus, arsenic, antimony, and bismuth, right? This, the bond angle is 104. Here the bond angle is 1 approx 90 degree, correct? This is the bond angle. Now let's talk about bond strength. Let's talk about the bond strength, right? N and H, P and H. Nitrogen, phosphorus. ठीक है, fine. Okay, so here bond strength. Nitrogen, this. Second period, first period. Third period, first period. Fourth period, first period. Fifth period, first period. Sixth period, and first period. Right? So, what is where the bond strength? What you know? You know that when the size is similar, then the bond will be stronger. When there's a large gap in the size, then bond will be weaker, right? So there's a large gap in the bond. There's a large gap in the size. So BH bond is the weaker. NH bond is the stronger, right? So what we can tell, what about the bond strength? Where the bond strength is maximum? Ammonia, phosphine, arsenic, antimony, and bismuth. Nitrogen, phosphorus, arsenic, antimony, and bismuth, right? This is the bond strength. Now, if this is the bond strength, same this concept you can use for hydrides of all the groups. This is the bond strength. Now, the next property is reducing behavior. Now, the next property is reducing behavior. The one who will dissociate H faster will be stronger reducing agent, right? Because reduction means reduction means addition of H, the one who will provide H will be stronger reducing in nature. Correct? So who is reducing nature? ठीक है, या फिर reducing character या फिर reducing power. So who has the best reducing power? Inverse. Bismuth, antimony, arsenic, phosphorus, and ammonia. This is the reducing power. Now next is basic character. Next is basic character. We know that basic character, we know that basic character is reverse of En, right? We know the basic character is reverse of En. So based on that, ammonia should be least basic, but this is not the case. The order is different. BiH3, sorry, the order is different. It means that we know that basic character is reverse of En. So bismuth should be highly basic, but the order is different. Ammonia is the strongest base, then phosphine, then for ammonia, phosphine, arsenic, bismuth, and arsenic, nitrogen, phosphorus, arsenic, bismuth, nitrogen, phosphorus, arsenic, antimony, and bismuth. ये हो गया order. This is the basic character order. And what is the reason? What is the reason here? The reason here is nitrogen being small in size, nitrogen being small in size, cannot accommodate lone pair, cannot accommodate lone pair. Hence, nitrogen wants to donate the electron, and that donating tendency is called basicity. So this order you can follow, this order you can follow for all the groups, not only for nitrogen. So I will write here again basic character. Basic character, ammonia is highly basic because the lone pair cannot be accommodated. Ammonia, phosphine, arsenic, antimony, and bismuth. Reducing character, which will reduce faster, ulta, bismuth, antimony, arsenic, phosphine, and ammonia. उसके बाद bond angle. After that, bond angle. Bond angle is maximum for ammonia, phosphine, arsenic, antimony, and bismuth. Bond strength, ammonia, phosphine, arsenic, antimony, and bismuth, right? This you can use for all this you can use for all the hydrides of group. तो ये है हमारा यहाँ पे सेम H2O, right? Night oxygen, H2S, sulfur, selenium, tellurium, and polonium. And basic character, polonium, reducing character, sorry, polonium, tellurium, selenium, sulfur, and water. Bond angle, where the bond angle is maximum, H2O, H2S, H2SE, H2TE, H2PO. Bond strength, H2O, H2S, H2SE, H2TE, and H2O. So same you can use here for this hydride of group 17 also, right? And this is very important. So now here, see, ammonia, this is the basic strength, and down the group bond angle decreases, bond strength increases, bond length increases, sorry, thermal stability, if they will become weaker they can be destabilized easily, reducing nature increases, basic character decreases, right? This you can use for hydrides of all the groups. This you can use for hydrides of all the groups. And what are the all the groups? Group number 13, 14, 15, 16, 17 and 18. ठीक है. Very, very important. NF3 is the only stable trihalide of nitrogen. In the exam, they can ask you which trihalide of nitrogen exists. NF3 is the only stable trihalide of nitrogen. Nitrogen do not form pentahalide. It does not form pentahalide. BIF5 is the only pentahalide of bismuth which exists. BIF5, this is the only trihalide of nitrogen. This is the only pentahalide of bismuth which exists. Trihalide except bismuth are predominantly covalent in nature. They can ask you BIF3 is what in nature? BIF3 is covalent. So NF3 only trihalide, BIF3 only bismuth, because if you will write this Cl5, chlorine, bromine, iodine, if you'll write like this, right? If you'll write like this, their size increases, is stability become less. After this, group number 16, oxygen family. Oxygen, sulfur, selenium, tellurium, polonium, and uh, livermorium, right? So these are non-metals. These are also called chalcogens. Chalco means ore, gen means generating. So these are also called as chalcogens, right? So oxygen, sulfur, non-metals, metalloids, and metals. Okay, fine. Now, except oxygen, all members are solid. In oxygen family, only oxygen is gas, all the members are solid. All these elements exhibit allotropy. For all of them, there is allotropy. Acha, oxygen shows anomalous behavior that we know already because of its small size, high En, and absence of d orbital. Atomic radii increases with increase in atomic number. Again, there is no exception. There is no exception for this. There is no exception for this. Down the group, size increases. No exception the size. Down the group, ionization energy decreases. Oxygen, sulfur, selenium, tellurium, and polonium. Again here, no exception. When we go down the group, ionization energy increases, decreases, and size increases. ठीक है. Oxidation state. Okay, we will do this. Okay, let's solve this question here. Yes. So this is the question. See again, I have told you last year, 2025 paper it is. and they have asked you this question. Hydrides are very much important. So do let me know the answer for question number 23. I'm giving you some time. Just solve it and tell me the answer for this. Okay. So what is the answer for this? Given below are the two statements. The boiling point of hydride. Acha. Oxygen, tellurium, sulfur, and this. Let me explain you this. So boiling point of this hydride is this. Oxygen, sulfur, selenium, tellurium, and polonium. Oxygen, sulfur, selenium, tellurium, and polonium. Right. So what actually happens? Who shows the H bonding? They show the H bonding, right? So H bonding boiling point depends upon two factors: intermolecular force of attraction, intermolecular force of attraction, or molecular mass, right? So what happens if this has H bonding and This has the maximum mass, right? So what should be the order for this? Water highest, then polonium, then tellurium, then selenium, and then sulfur, right? Why? Because melting boiling point is more when mass is more, right? And why this is high? Because of H bonding. So what is the answer for this question? What is the answer? The boiling point, this order seems correct. Statement number 1 correct. On the basis of molecular mass, H2O is expected to have lower boiling point. That is true than the other member. But due to the presence of extensive H bonding, H2O has a higher boiling point. Correct. Boiling point depends upon two factors: molecular mass and uh, intermolecular force of attraction. So if there is a if molecule has if the molecule has H bonding, it has the strongest intermolecular force of attraction. So if the molecule has H bonding, it means the boiling point is highest, and if the molecular mass is least, it means molecular boiling point is least. So what is the answer for this? Statement 1 is true, and it is uh, statement 1 is both statement 1 and 2 is true. Even this is the correct explanation also. Which the following does not show -2 oxidation number? Who will not show -2? Oxygen, polonium, sulfur, tellurium. Oxygen, sulfur, selenium, tellurium, polonium. Polonium is a metal. Metal will not gain 2 electrons and will show -2. Non-metals gains electron. Metals lose electrons. Polonium will lose, it will not gain. So answer is polonium, right? So these were the questions which I've asked from P block in the last year 2025. Thermodynamics, equilibrium, D and F, coordination, haloalkanes, electrochemistry, chemical kinetics, amines. Hmm. Polonium does not show -2 because it is a metal. It will only gain, and this is the correct order of the boiling point. So here I will also write the order of the boiling point in this. What is the order of the boiling point? I'll write here the boiling point order also. Boiling point order. Who has the highest boiling point? Water, H2S, oxygen, sulfur, selenium. No. Oxygen, then polonium, oxygen, sulfur, selenium, polonium. Oxygen, sulfur, selenium, tellurium, polonium. Hmm. Okay. Now let's move here. Yes. Now oxidation number 1. Oxidation +2 increases as we move down the group. Oxygen shows -2 to +2. Sulfur, selenium, tellurium show +4 and +6. And +4 and +6, the stability is more as we go down the group. As we go down the group. And the reason for this is inert pair effect. The reason for this is inert pair effect. Stability of +4 is more and +6 is less. +4 group 16 elements show, +6 shows oxygen and fluorine because they are high electronegative element, they can withdraw the electron more. Compound in +4 and +6 are covalent in nature. Acha, you guys know the Fazan's rule. You know the Fazan's rule. What is Fazan's rule? For covalent nature and for ionic nature, small size of cation, large size of anion, more charge. ठीक है. So plus 4 and plus 6, they have more charge. Hence, they are covalent in nature. They react with hydrogen to form hydrides. Again, the same hydride. Bond angle for this is 102 degree and 8 minutes, and for them it is nearly 90 degree. Okay. Bond length increases, thermal stability decreases, acidic character increases. This we have discussed earlier and is very important also. Now, reaction with oxygen. They react with oxygen, and O3 and SO2 are gases. O3 and SO2 are gases. Reducing property, decrease from SO2 to tellurium oxide. SO2 is reducing in nature, tellurium is is a oxidizing in nature. TeO2 is oxidizing and SO2 is reducing in nature. Reaction with halogen. When they react with halogen, they form EX2, EX4 and EX4. Stability of halides decreases because fluorine is small in size, right? So this can make a better stable compound. Iodine is a very large in size, so it can disperse, diffuse. They form dichlorides and dibromides. SF4 is a gas, SeF4 is liquid, and TiF4 is solid. Now next, among the hexahalides, hexafluorides are the only stable halides. Among the hexahalides, hexafluoride is only stable. It means they can ask you OF6 exists or maybe SF6 exists, but why not SCl6? Because chlorine is very large in size. 6 chlorine sulfur cannot arrange. So which one is more stable? SF6 is more stable. All hexafluorides are gases in nature. Monohalides exist as dimer. Monohalides matlab SF, mono single halides, they exist in dimer. S2F2, S2Cl2, S2Br2, Se2Cl2. These dimeric forms undergo disproportionation. Plus 2 say plus 4 and 0. Okay, they can show disproportionation. Group number 17. Group number 17. Now let's do group number 17. Okay, so group number 17. Fluorine, chlorine, bromine, iodine, non-metal, arsenic and this. These are radioactive and metals. These are halogens as their salts are usually found in seawater. Then physical state. F2 is a gas, Cl2 is a gas, Br2 is a liquid and I2 is a solid. The color of halogen is due to the absorption of visible light by their molecules, resulting in excitation of outer electron to higher energy level. Remember these colors because they have mentioned specifically physical and chemical behavior. So physical state may remember the color. The color depends down the group: pale yellow, greenish yellow, reddish brown, and violet. As you go down the group, color deepens. Correct. Halogens are diatomic covalent compounds. These elements do not show allotropy, they do not show catenation. Anomalous behavior of fluorine is due to small size, high En, non absence of d orbital, and higher positive reducing potential. Anomalous behavior of fluorine, these are the reasons. Now, the size, no exception, no exception in the size. As we go down the group, size decreases, size increases, and ionization energy, as we go down the group, ionization energy increases. Electron affinity, this is very important, and this is very important. Chlorine has high affinity, electron affinity is high. The reason being, chlorine has larger size, chlorine has larger size, comparatively more attraction, comparatively more attraction than bromine and iodine. Chlorine has larger size, comparatively more attraction than bromine and iodine, larger size than fluorine. So this is the reason then chlorine can attract electron, and it can also have enough space. So that's why please remember this sequence. They can ask you the question on this because it is exception. En is directly proportional to inversely to size. Bond length, very important. Important. Bond energy, very important. Chlorine, bromine, chlorine, iodine. Fluorine, fluorine, small in size, the repulsion is very, very large in small fluorine. So this fluorine is weaker than bromine and chlorine, and iodine is weaker than this. Please remember this sequence. The low value of heat of decision energy of fluorine is due to the non-bonding electron repulsion. Melting point and boiling point. Whose melting point is highest? Mass more. If the mass melting point is directly to mass, more melting point. Okay. Chemical behavior. Fluorine is the most electronegative element. Fluorine is the most electronegative element. So it always show -1 oxidation number. Fluorine is the most electronegative element. It always shows -1. In fluorine, the d orbitals are not available. Yet this we have done already. The anomalous behavior. Oxidizing nature. Non-metals, they lose electrons. No. Non-metals, they gain electron. Correct? If they gain electron, non-metals, if they gain electron, they get self reduce. Hence, they work as oxidizing. Okay? Hence, they work as oxidizing. So, metals and non-metals. Metals are hmm, okay. Okay. F2 is a stronger oxidizing agent among all the halogens. In general, halogen oxidizes halide ion of higher atomic number. Reactivity, okay, we'll do this. Just I'm giving you some questions. Let's solve these questions. No, not this. Hmm. Okay, this one. Can you guys tell me the answer for this? Just tell me the answer. I'm giving you 2 minutes. Solve this. I have explained this. Just do let me know. And it is very important. The nature of oxides. Okay, so I have given you enough time. Do let me know what is the answer for this. Carbon monoxide is neutral, barium oxide is basic, aluminum oxide is amphoteric, and this is acidic. So I have told you metals basic, non-metals acidic, and metalloids they will show amphoteric, right? So quickly come here and we'll finish this. All halogens are chemically very reactive element. They react with metal and non-metal to form halides. The reactivity of halogen goes on decreasing on moving down the group. Okay, so reactivity, who is highly reactive? Fluorine. Non-metal reactivity, non-metal reactivity based on losing, based on gaining electron. So who will gain the electron, which is the smallest one? And metal is reactivity is about losing electron, correct? Losing electron. So who will lose the electron faster? The one who is large in size. Who will gain the electron faster? Who is small in size? The high reactivity of fluorine is due to the weak FF bond, extremely high oxidizing nature, and electronegativity. Fluorine is also called superhalogen because FF bond is weak. FF bond is weak. It can be broken easily. With hydrogen, they form HF, HCl, HBr, HI again. Bond length, thermal stability, reducing character, acidic character. Acidic character is very important here. HI can be broken easily and can be converted into H plus and I minus. So this is highly acidic. After that, reaction with oxygen. EPIS, they form these oxides. Fluorine form only two type of oxides. Oh, chlorine forms a larger number of oxides. Chlorine, bromine, iodine, various type of oxides. The oxides in the higher oxidation state are more stable than the lower oxidation number. The stability of oxides formed by halogen varies like this. This is called middle row anomally. These are least stable halogen oxides. They are very powerful oxidizing agent. O2F2 is unstable and useful in removing. Very important. They have asked this question in PYQ. O2F2 is unstable and used in the removing Pu as Pu6 from the spent nuclear form, nuclear fuel. So they have asked the question which oxides of fluorine is used to remove to to remove Pu from nuclear fuel. Remove Pu from nuclear fuel. So what is the answer for this? Now, chlorine water. What does chlorine water does? It is oxidizing in nature. It is oxidizing in nature. -2 to 0, +4 to +6, +5, +3 to +5, like this. Used in the purification of drinking water, chlorine water, used as a bleaching agent because of its oxidizing nature. Cl2 is used as a bleaching agent. Cl2 is used as a bleaching agent due to its oxidizing nature. Used as germicide and disinfectant. Pseudohalides. What are pseudohalides? What are actually pseudohalides? Pseudohalides are one. Pseudohalides are not actually halogens, but they behave as halogen. They will form single bond like that. So pseudohalides are what? They are uninegative. They have properties similar to halide ions. They consist two or more atoms like nitrogen. They give salt resembling halide salt. For example, this pseudohalide ions has a corresponding halogen. Okay, so Cn, SCN, OCN. Okay, so they will form a dimer like F2, Cl2, Br2. These are pseudohalides. Cn minus, SCN and OCN. These are pseudohalides. The well-known pseudohalide is Cn. It resembles chlorine, bromine, iodine in the following respect. It gives acid with HCN. It can oxidize to form molecules, cyanogen. It is forming large number of complexes similar to halide complexes. So these are the pseudohalides. They behave like they behave like their behavior is similar to halogen. Now next, interhalogen compounds. Mixing of two halogen is called interhalogen. Halogen combines with these themselves to form a number of interhalogen compounds: X, X dash, X, X3 dash, X, X5 dash, X, X7 dash. So these are the interhalogen compounds, halogen reacting with halogen. Okay. So where X is large in size, halogen, and X should be large and X dash should be small, then only this can hold this, right? For example, you cannot uh, form like this, right? The answer, it has to be like this one. These are the interhalogen. These are the interhalogen. Interhalogen compounds are more reactive than halogen due to bond polarity and less bond dissociation energy. These compounds can be used as non-aqueous solvent, used as a fluorinating agent. ClF3 and BrF3 are used for the production of UF6 in the enrichment of this. Again, the very important, which interhalogen is used for the enrichment of uranium? In enrichment of uranium, uranium, what is the answer? ClF3 and BF3, BrF3 is used. Now next, test of halide ions. This we do not need to do. Now next is group number 18, the last group: helium, neon, argon, krypton, xenon, radon, and organocin. Oxidation number they show +2, 0, +2, +4, +6, +8. Noble gases we know it is inert due to stable configuration and high oxidation number, and because it is very tough to remove the electron from noble gas. Then okay, then after that, first inert gas compound was prepared with Neil Bartlett, and it was similar to xenon. Neil Bartlett, PT, F6. This is similar to this. First inert gas compound was this. Similar to this was the first inert gas compound they have prepared in the lab. Physical state, these are gases, colorless, odorless, tasteless. Why they are gases? Because they do not combine with the another atom of noble gas, and that's why these are colorless, odorless, tasteless. These gases neither burn nor support in burning. Okay, since their combining capacity is very low, they exist as single atom, hence they are monoatomic. Van der Waals force of attraction between these atoms, that's why, which increases their ability to polarize. The ease of liquefaction of these gases increase in their atomic weight. So helium, neon, argon, krypton, and xenon, which can be liquefied easily. The answer is xenon is most liquefiable. Okay. Now next is what? Melting point. As we go down the group, the mass increases, melting point increases. Boiling point also mass increases, and melting point and boiling point both increases. No exception in this. Solubility in water, these gases are sparingly soluble because they do not form bond with water. Solubility in water increases with increase in atomic number, because as we increase the atomic number, the van der Waals force increases. If the van der Waals force increases, so attraction will increase. If attraction will increase, solubility will increase. Electrical conductivity. These gases have fairly high electrical conductivity. They produce characteristics colored light when electrical discharge is passed through the atom at low presence. ठीक है. उसके बाद है what are the some compounds. In the exam they can ask you what is the shape. They have asked already what is the shape, what is the hybridization. XEF6, XEF6 sp3d3, distorted octahedral. Then XEF4, it is square pyramidal. This is square pyramidal. One, no, no, not square pyramidal, sorry. This is square planar, two lone pair and four bond pair. XEF2, sp3d, linear. This is linear. Then we have, these are the hybrid, these only mostly compounds of xenon exist, and these are the compounds. There are very high chance that they can ask you hybridization and lone pair bond pair, because this topic is related to chemical bonding also, and it is related to p block also. So I hope you guys know how to find the hybridization. Then after that, the noble gases. What are the uses of noble gas? What are the uses of noble gas? They are non-inflammable. They don't catch fire. Filling balloons for meteorological observation. Used in gas-cooled nuclear reactors. Liquid helium is used as cryogenic agent for carrying out various experiments at low temperature. Used to produce and sustain powerful superconducting magnet, which form an essential part of modern NMR spectroscopy and MRI. Used as a diluent for O2 in modern diving apparatus, as it has very low solubility in blood. So these are the uses of noble gas. Inflammable, filling balloons, used in gas cooled nuclear reactors. Liquid helium is used for a cryogenic agent for carrying out various experiments, because they do not react, because helium does not react. Used to produce and sustain powerful superconducting magnet, which forms an essential part of modern NMR spectroscopy and MRI. Used as diluent for O2 in the modern diving apparatus. Again, the reason is, if you will dilute oxygen with noble gas, then what will happen? It will not react. After this, used in discharge tubes and fluorescent bulbs. Neon bulbs are used in botanical garden, mainly used to provide an inert atmosphere in high temperature metallurgic process like arc welding. Used in labs for handling substances that are air sensitive. What are the use of for xenon and krypton? Used in light bulbs for specific purpose. So yes, so here we have revised the whole P block, group number 16, group number 13 to group number 18. My suggestion would be stick to the portion, stick to the portions which is given in the NCRT syllabus, stick to that syllabus. Do not just read random stuff, and read NCRT, read NCRT, uh, read NCRT by following the portion, by following the portion, right? Okay. Then remember the exceptions. Wherever there are exceptions, make a note of exceptions. Make a note of exception. And and revise frequently. And revise frequently. And revise frequently, because if you will not revise P block, you are going to forget the details, the information. So this is the information based chapter. I would suggest that you should revise it frequently. So again, stick to the portion, read NCRT following the portion, make a note of the exception, list of the, make a list, better, make a list of exceptions and revise frequently. Okay, so then you will be able to cover this P block. So thank you very much for listening this class. So I hope this lecture was helpful, and I am ending this lecture here. Thank you.